Okay, so this video is going to be a pretty short one. We're just going to talk really quickly about how to make Lewis dot structures and Bohr diagrams. The assignment that goes along with this, there's a lot of drawing involved, so I'm not actually going to make you guys do it while you're on quarantine. If you have a printer, want to print it out, and then go ahead and get through it, then you can. But it won't take too long to catch up on once you get back, and it'll be good to make sure we know how to do this before you take the test on this unit. So we're going to talk about Bohr diagrams, and then we're going to talk about Lewis structures. We'll go relatively quick through them. I'm going to do about 3 examples of each. They're not too terribly difficult, I don't think. But I want to make sure that you guys have at least seen these, know what they look like, and then when we get back, we can practice drawing them. So we're going to start off by doing the Bohr diagram. So we're going to work with Bohr diagrams to start. That's these ones for beryllium. So beryllium, that's right here. It's element number 4. So we know that it's going to have 4 electrons and 4 protons. There are a couple of different ways to draw Bohr diagrams, specifically with the nucleus. With elements really small like this, we can draw what's called a full Bohr diagram, where we actually put the pluses. So we're going to draw out 4 pluses for my protons. That's going to go right here. So this is my nucleus. Then the actual point of a Bohr diagram is to draw the energy levels and put the electrons in as dots. So the first energy level holds just my 1s orbital, which holds 2 electrons. So I'm going to put 1, 2 electrons, and then I'm done with my first energy level. Because I have 4 electrons, I've used 2. That means I have 2 left. We have to go to my second electron or energy level. This holds the 2s orbital and the 3 2p orbitals. It can hold up to 8. We only need 2, so we're going to put 1, 2, and there we are done making the Bohr diagram for beryllium. So basically what Bohr diagrams do is they show us all of the electrons in an element, and they show how they're arranged. So it's kind of like an electron configuration, but all kind of visualized. It's all just kind of in one specific spot. It's important to remember that Bohr diagrams is not actually how electrons behave or what orbitals look like, but this can be really helpful for knowing how many electrons are in each shell and what we're doing with them. So let's look at a more complicated one. Let's drop down here and let's do sulfur. So sulfur, that's element number 16. So you have 16 electrons. I'm just going to write sulfur in the center. I'll do the third way on the third element that we do. So we've got sulfur in the middle. Again, first energy level, we can only hold 2 electrons, so we're going to put 1 here and 1 here. It doesn't really matter where you put these 2. I just put them on opposite sides because it looks the nicest, but it doesn't really make a difference. Then we draw our second energy shell, or energy level. This one's going to hold 8. Now, this time around, I'm actually going to draw electrons like this, and it's just to show that they're paired, because it helps me keep track of them. You can spread them out if you want. You can put them like, so you can have, 4 corners and then 4 sides, whatever you want to do, as long as you have 8 electrons in there. It'll look a little weird if you put them all to one side, but that's up to you, I guess. So we used 8 in our second shell, 2 in our first shell, so we have 6 left to go. Total of 10 already in here. We have 6 left. So we're going to draw our third energy shell, which we, of course, have the 3s orbital and the 3p orbital. We need 6 more electrons, so I'll put 1, 2, 3, 4, 5, and 6. And now I'm done. I've drawn the Bohr diagram for sulfur. So again, it shows me all of the different electrons at all of the different energy levels. This is kind of helpful for like visualizing how many electrons I could theoretically get off easily. So like I could take these first 6 off with, it'd be a lot of energy, but I could do it. Trying to get at some of these inner ones would be really difficult to do. So we've kind of got 10 shielded electrons that are hard to interact with. And again, it's just a visualization tool. This isn't actually how orbitals are spread out, but it is kind of a nice representation of how they pack in on each other and how we can kind of shield inner electrons using these outer ones. The last element we'll look at is bromine, and we're doing this mostly just to see what happens when we start adding in d orbitals. So bromine, it's element number 35. So you've got 35 electrons. This time what I'm going to do for the nucleus, I'm going to write 35 plus. So that tells me that there are 35 protons. That is the element bromine. This is just another way of doing that center. First energy shell, as you can guess, that's our 1s orbital. We've got 2 electrons in it. Boom. Second energy shell, we've got 2s and 2p. So again, 1, 2, 3, 4, 5, 6, 7, 8. Okay, then we got our third shell. So third shell, again, we've got 3s and the 3p. So you got 1, 2, 3, 4, 5, 6, 7, 8. So at this point, we've used 18 electrons. We still have 17 to go. So we can kind of draw this out. Boom, we'd have 17 electrons left. Now, for a minute, I'm going to take a quick break and I'm going to show you guys the electron configuration for bromine to remind you of what that looks like. So we start with 1s2, 2s2, 2p6, 3s2, 3p6. Then we've got 4s2, 3d10. That's going to be an important one. And then we have 4p5. This is where the last of my electrons go. So we are going to need that fourth energy shell next. So that's going to come up. We're going to draw that. And you can probably see why we don't usually do big elements when we're drawing Bohr diagrams. It becomes a pain very quickly. So we're going to need to put 2 electrons in here. We'll go 1 and 2. And then we've got this 3d10. So we need to put 10 electrons in the 3d orbital. And the 3d orbital is part of that third shell, even if it is easier energy-wise to put things into 4s. These do go on the third shell. So I'll go back to my third shell and I'm going to add 10 electrons to it. So go 1, 2, 3, 1, 2, that's 5, 1, 2, 3, 1, 2, that's 10. So that means that I now have 18 electrons in my 3D shell, or in my third shell, which is actually accurate. It's how these get held. If you add your 3s2, your 3p6, that's 8, and then your 3d10, that's 18. Then we have 5 more to go in our 4p5, so we'll come back up here. We'll go 1, 2, 3, 4, and 5. And there we go. We've drawn the Bohr diagram for bromine. So Bohr diagrams, they show all of the electrons involved. Drawing a Bohr diagram for something like, let's say, a seabordium would be absolutely terrible. It would take forever. It would look really messy. It wouldn't be particularly helpful. So these are kind of the way that atoms were conceptualized for a really long time. In general, in chemistry class, this model is actually not particularly helpful. What we really mostly care about is valence electrons, and that's where Lewis dot structures come in. So I think you guys like these ones better. They're a lot simpler. Let's start. We'll go ahead and do some of the same elements just so that we can look at them. So we'll start with beryllium again. So beryllium, again, has 4 electrons. But right now, for Lewis dot structures, so we moved on to these ones, we only care about the valence electrons. Valence electrons can be kind of determined by the family. So this family, the alkali metals, they all have just 1 valence electron. Alkaline earth metals have 2. The boron family has 3. Carbon family has, let's see if we move this, 4. Nitrogen family has 5. Oxygen family has 6. And the halogens have 7. And of course, these have 8. So these are the valence electrons. Generally, the number for the transition metals is somewhere between 2 and 3. It can change a little bit, so we don't worry about those. I won't have you do too many dot structures for these. And if I do, I'll tell you how many valence electrons they have. But beryllium, being right here in an alkaline earth metal, is going to have 2 valence electrons. So 2 valence electrons. So what we do when we're doing the dot structure is we first write the chemical symbol kind of big. And then all we have to do is place the valence electrons as dots around the element. So we'll put 1 here, and we'll put 1 here. And that's it. That's the Lewis dot structure for beryllium. We're done. Easy peasy. It's just the chemical symbol with the number of valence electrons put around it. Now it does get a tiny bit more complicated. So if we take sulfur, sulfur is right here. It's in the oxygen family. It has 6 valence electrons. 6 valence electrons, yep. Sorry, counted wrong. So we have 6 valence electrons in sulfur. So we'll draw our S. We'll put 1 here, 1 here, 1 here, 1 here. Now, last time I was saying that I would split up the electrons just because it kind of looked nice. This time it actually does matter a little bit. We can move them around when we're using this, but we're actually going to use these types of models when we start talking about covalent bonding. But for now, it doesn't really matter, but I am going to put things on opposite sides generally. And that's just because in a neutral state, if this atom isn't reacting, its electrons, the pairs are going to get as far away from each other as possible. So technically, you could also write it as the 2 dots on the sides, and then 1 dot on the top, and 1 dot on the top. Just don't give me Bohr diagram or Lewis dot structures that look like this. Have 2 electrons and they're both on one side, or like, we have dot, 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 and then single dot, single dot. This isn't technically wrong, but it's also wrong. So in general, if you have just like 2 pairs or 2 electrons or whatever, make sure you split them across. So then if we look at bromine, again, we take bromine. Bromine's in this halogen row, so it's got 7 valence electrons. So we need to just write the chemical symbol for bromine. We're going to 1, 2, 1, 2, 1, 2, and 1. And ta-da, there's the Lewis dot structure for bromine. So Lewis dot structures are really simple. They just tell us the valence electrons, they tell us how they're arranged. And when we get to chemical bonding, they'll kind of tell us how many bonds that things can make and stuff like that. But we'll worry about that when we get there. So for right now, you just need to be able to draw Bohr diagrams and Lewis dot structures. And so just to go over them one more time, I'll do a simple one. We'll do lithium. So lithium has 3 total electrons, 1 valence electron. So the Bohr diagram, and the dot structure for lithium will look like this. So we'll do Li in the center, our nucleus. We're going to have energy level 1. It's going to have 2 electrons in it. And then energy level 2 with just 1 more electron. The dot structure, we just look at that valence electron. There's just 1 of them, so it looks like that. So it's worth knowing which one is which. We should know the Bohr diagrams are the one that show the energy levels. They show all of the electrons. Dot structures just show the valence electrons, and they don't show any of the inner energy levels. So that's important to note. But otherwise, this is all we're really talking about tomorrow in class. We're going to have a project in it. I'll put it in Google Classroom. I'm not 100% sure what it's called again right at the moment, but you'll see it. Don't worry about it while you're at home, but make sure that you know how to do it so that when you do get back and I can give you a paper copy, you can start filling these in pretty quick. I think that's about it.